Welcome to HBOT Journal, a channel dedicated to understanding hyperbaric oxygen therapy through evidence, science, and experience.
When we think of oxygen, we think of life itself, right? We breathe it every single moment. We don't even have to think about it. And because it's so familiar, it's really easy to assume it works in a simple way, that getting more oxygen is just about breathing deeper or from a more concentrated source. But in reality, the way oxygen actually gets to our tissues is, well, it's a lot more structured than that. Okay, let's dive into this. So, here's our roadmap for this explainer. We're going to start with how oxygen normally travels around the body. Then we'll get into the natural limits of breathing. We'll also clear up how oxygen moves by diffusion, not force, and then take a look at how pressure can change the physical conditions. And finally, we'll see how this all fits into a structured medical approach and clear up some common misunderstandings along the way.
All right, so first things first. Before we can really get into the exceptions, we need to understand the rule. So let's take a look at the body's standard and really highly organized delivery system for oxygen under just everyday conditions.
It all kicks off in the lungs. When you take a breath, oxygen floods into millions of these tiny little air sacs called alveoli. Now, these sacs are right up against very small blood vessels, and this is where the handoff happens. Oxygen passes from the air you just breathed directly into your blood.
You can think of this journey as a really neat four-step process. First, oxygen enters the lungs. Second, it crosses over into the bloodstream. Third, it binds onto red blood cells for the ride. And fourth, it travels out to all the tissues in your body that need it to work. It's an incredibly reliable system that's just running in the background, supporting everything we do.
Now, the main player in this journey is a protein called hemoglobin. Think of it like a dedicated taxi service inside every single red blood cell. It is incredibly good at grabbing oxygen in the lungs and then dropping it off exactly where it's needed. But, and this is a really crucial point, just like any transport system, it has physical limits.
And that brings us right to the heart of our topic. If this system is already so efficient, can we just give it more fuel? Why doesn't just breathing more concentrated oxygen automatically mean more gets delivered to our tissues, at least under normal pressure?
This is the assumption a lot of us make. And it seems totally logical, right? If the body needs oxygen, just give it more. But as it turns out, biology and physics have something to say about that. So take a look at this. What's so fascinating is the limit this chart shows us. When you're breathing normal air, which is about 21% oxygen, your hemoglobin is already around 98% full. It's almost at capacity. Now, if you breathe 100% oxygen at that same normal pressure, you only close that tiny little gap to get to about 100%. So, the key takeaway here is this. There's a ceiling. Once those hemoglobin taxis are all full, they just can't carry significantly more no matter how much extra oxygen is floating around at normal atmospheric pressure. The main delivery system is already working near its absolute max.
Okay, so let's get into another common idea. How does oxygen get from the blood into the tissue itself? Well, it's not a forceful thing. It's actually a very quiet, passive process that's governed by a fundamental law of physics.
It's really tempting to think of oxygen as being pushed into our tissues, kind of like water getting forced through a pipe, but that's not really how it works. The real principle here is diffusion. Oxygen just naturally moves from an area where there's a lot of it, like in the blood, to an area where there's less of it, like in the tissues. It's all about balancing things out.
This phrase just sums it up perfectly. Oxygen follows conditions, not instructions. You can't order it to go somewhere. It just responds to the physical environment around it. No force, no instructions, just physics.
So if just adding more oxygen has its limits, what other factor could be in play? Well, this is where pressure comes in. And pressure isn't about pushing. It's about changing the entire environment that the oxygen is in.
Let's just make sure we're on the same page with a couple of terms. First, we have oxygen concentration. This is pretty straightforward. It's just the percentage of oxygen in the gas you're breathing. It's one piece of the puzzle.
And then we have pressure. This is a completely separate variable. It describes the physical conditions of the whole environment. You can think of it as changing the fundamental rules of the game for how gases behave.
So let's circle back for a second. At normal, everyday atmospheric pressure, our trusty hemoglobin is doing almost all of the heavy lifting. That's our primary transport system. But here's where changing the pressure changes the whole game. Under higher pressure, the physical laws shift a bit, and oxygen can do something new. It can actually dissolve directly into the plasma. That's the liquid part of your blood.
This creates a whole new way for oxygen to be physically available in the body, totally separate from the hemoglobin carriers.
And this is a really crucial distinction to make. Pressure doesn't force or direct oxygen to go anywhere. It simply changes the physical conditions, which then increases the availability of oxygen by letting it dissolve. It's a change in the physical behavior, not a guarantee of a specific outcome. Understanding these physical principles really helps explain why medical applications that involve oxygen are so carefully controlled. It's never about just one single factor. It's about a complete interacting system.
You know, in any structured medical context, professionals are looking at the entire picture. How's the person breathing? How's their circulation? What's the pressure? How much time are we talking about? And, very importantly, who is supervising? All of these things interact with each other.
And that's exactly why any medical use of oxygen is treated like a regulated medication. It has to be planned, structured, and supervised. It's all about understanding how these physical conditions can influence biological systems in a very controlled way, not just, turning up a dial.
Now, it's really important to be clear about what these principles don't mean. Getting the physics helps us avoid some common and potentially risky misunderstandings. So let's just tackle these directly. Just because pressure changes physical conditions, that does not mean higher pressure is always appropriate. Oxygen is not a casual, risk-free tool. It has real risks when it's used incorrectly. And most importantly, unsupervised use is never a safe shortcut. These concepts really belong inside a clinical framework.
At the end of the day, this is the essential rule to remember. Different designs exist for different contexts under appropriate supervision. Context and professional oversight are just non-negotiable.
So, to wrap it all up, oxygen is absolutely vital, but its delivery is a structured process with real physical limits. Pressure is a variable that changes physical conditions, not one that guarantees specific outcomes. And this is why any medical application has to be approached within a controlled, supervised, and professional environment. The guiding principle here should always be education before expectation.
To continue learning, explore the HBOT Journal channel.